So, in the previous class, we introduced Poisson brackets, right, as a very useful tool, not just in classical mechanics, also in quantum mechanics. At some point, you will see, and you will use them, right? So we define them as at the first view, kind of very strange tool, but happens to be very useful, and we can basically reformulate classical mechanics in terms of Poisson brackets, right? And in the previous class, we basically derived, right, what is called fundamental Poisson brackets. Let me write them down because we will need these today. And also, we rewrote Hamilton's equations in a nice, elegant, symmetrical form using Poisson brackets. Right, but first, fundamental Poisson brackets, you remember, so if you write, which subscript I use, Qi and K, Qi, Qk, right, of course, we assume that these are canonical variables, right? So, of course, Hamilton's equations are correct. So, this is 0. It doesn't matter if indices are the same or different, right? It's the first fundamental Poisson bracket. Then the second, Pi Pk also must be equals to 0. And again, of course, they are written in terms of Q small, P small, right? You see, in terms of original variables. And the last one, fundamental Poisson bracket, it's a Qi Pk equals to symbol Kronecker Ik. So it is 1 when I equals 2k. So these are fundamental Poisson brackets. Okay, let me and write it down. So fundamental Poisson brackets. Right. And at the end of the class, we also rewrote Hamilton's equations. And as I said, in a nice, elegant form. You know what? I'll probably write them here. Maybe I separate like this. Right. And so what Qi dot equals to the Poisson bracket between Q and the Hamiltonian, right? Qi and the Hamiltonian, right? So that's the first Hamilton's equations. And the second, of course, Pi dot, it looks exactly the same except for instead of Qi's, we have Pi's. Right. So Hamilton's equations. So now, what's next? What if we have, okay, let me check if I, mention everything which I was planning. What if we have some function, u, for example, which describes something about your system, right? And let's say you want to test if this function is a constant of motion or not, or integral of motion. So how can we check that using Poisson brackets? So now that's the next goal. And then we will talk more about these Poisson brackets. So let me write this down. Yeah. Okay, I will probably put a new bullet small in, right? So Poisson brackets can help to find a constant of motion. So Poisson brackets can help to find a constant of motion. To find a constant of motion. And of course, how? Let's see. So let's assume that we have some function u, as I said, function which describes your system, which is a function, of course, of q, p, and t. Okay, the whole set of q's, the whole set of p's, and possible time dependence, right? And so what does it mean, constant of motion? It doesn't change in time. So let's look at the total time derivative of this function with respect to time, right? Nothing fancy. So let's write, so du over dt, and of course first we will, yeah, I can fix it, du over partial derivative with respect to t, and plus, and again, yeah, this is the whole set of q's and the whole set of p's. I just didn't write the subscript. Right, okay, I can put, in which subscript I use? I, okay. So will be partial derivative of u with respect to qi, and then qi dot plus partial derivative of u with respect to pi, pi dot. Right, so that's just calculus. And now let's recall the Hamilton's equations in the old form. In the old form, right? So which is qi dot equals to partial derivative of h with respect to pi, and pi dot equals to minus partial derivative of h with respect to qi, right? So if we use that, then this is equal to dh over dpi, and this is equal to minus partial derivative of h with respect to qi, right? As a result, what are we getting? I'm just lazy to rewrite it, right? To save space. So it will be what? du over dq and dh over dp. Then there will be minus over here. And we will have now du over dp and dh over dq. It's a Poisson bracket of u and h. Poisson bracket of u and h. Right, so, okay, with this summation. So it's a Poisson bracket of u and h. U and h. It sounds like University of New Hampshire, UNH, right? Every time when I come to this point, UNH, and immediately, New Hampshire. And so we can write, so du over dt, total time derivative, it's a partial derivative, plus u and h. And in order for u to be a constant of motion, it must be equal to 0, right? So we're getting the condition. So if this is correct, then your function u is a constant of motion. Plus, we can easily sort of remove this because it's search for an explicit time dependence. If you have function u, immediately you can see, okay, if there is a t or not in that function, right? And if there is no explicit time dependence, then condition gets simplified to just a Poisson bracket of u and h, right? So, and if, which way I wrote it, if u doesn't have an explicit time dependence, explicit t dependence, so then of course condition gets simplified. All right, so du over df partial derivative equals to 0, and then of course we are getting that a Poisson bracket of the candidate and the main function of which describes system Hamiltonian must be equals to 0. So u is a constant of motion if it's sort of like a like an interview, personal communication of the candidate and the biggest boss of the system, right? If it gives 0, yeah, it's a constant of motion. Right. What is also interesting, right? It's sort of similar to this equation. So QH, PH, here we have UH, right? That's all. Just trying to find some similarities, right? All right, so that's the condition. So if this is true, then U is the constant of motion. Right? If this is true, then U is a constant of motion. Right. So now we know how we can find if something is an integral of motion, a constant of motion. So next, very important, next part. Invariance of Poisson brackets under canonical transformations. What it means. So let's assume that we have two functions describing a system. Instead of U, let's assume that we have function f and function g. Both describe something about the system, right? And so if you construct a Poisson bracket out of these two functions, f and g, right? And first calculate it in old canonical coordinates, q small, p small, and then use canonical transformations, move to q capital, p capital, and calculate Poisson brackets out of the same functions q, f, and g, the values of these Poisson brackets will be equal. But again, it's only true if you use canonical transformations, if you move from a nice place to a nice place, right? Only in that case, the value of Poisson brackets stays the same, right? Let's prove it. And it will lead us to a very nice test which can be used to prove if a transformation is canonical. And we are going to use that those conditions, those tests, in order to convince ourselves if this or that transformation is canonical. It's very, very useful test. Okay, but first, let me state the statement that Poisson brackets are invariant under canonical transformations, and then we will prove it. Right. And it also adds one part to your homework. Okay, I will show you where and what. Okay, so now I need to put a new bullet probably over here. Right. And let me write sort of the title of this section, which is important. So the Poisson brackets are invariant under canonical transformations, right? PB, Poisson brackets, are invariant under canonical transformations. Let me write underneath canonical transformations. So, the sort of form, the values of Poisson brackets are independent of the set of canonical coordinates, which is basically the same, potato, potato. All right, okay. So if we have this transformation from q small, p small, again, here it means it's a set of q's and set of p's, right? And I runs from 1 to n, right? And you move from this to q capital, p capital, and let's assume that we have canonical transformation. All right? And so then, and as I said, if you have two arbitrary functions f and g, of course, well behaved, which describe the system. Probably I should write something about this one functions, right? Arbitrary functions and consider two arbitrary functions f and g. F capital, G capital. Of course, they must be well behaved, right? So continuous. You can differentiate them as many times as you need or you want, right? And so if this is true, then if you construct Poisson brackets out of these two functions in the original set, old set of canonical coordinates, it must be equal to Poisson bracket out of the same two functions, but now, of course, calculated in terms of Q capital, P capital. So, invariant. Okay, so now there will be somewhat tedious proof, right? Actually, it's not that bad. And yeah, I think I mentioned everything. Yeah. So now let's start with. So basically, I will start from this, and then eventually I need to get that. Okay. So F G in terms of Q small, P small, and of course by definition. You remember definition. I think subscript I use K. Okay. Summation over K, and then partial derivative of F with respect to Q K, partial derivative of G with respect to PK, then minus, and then we change the order of differentiation, right? So partial derivative of F with respect to PK and partial derivative of G with respect to QK. So that's by definition. Now, let me open my explanation box. Right. And let's look at function G. Of course, function G, it's a function of what? We can write as Q capital and P capital. And I think I use subscript L. Yeah. Of course, we assume so canonical transformation. So we have transformation equations, right? So available, right? So in this direction and in the opposite direction, right? So we just, the goal is to prove this. So we assume the rest. So transformation equations are given. So we know how we can move from Q small to small variables to capital variables and in the opposite direction. So of course I can write it as a function of Q, which is, since we have transformation equation, we can write it, this Q capital in terms of Q small. Small variables, Q small and P small. And also, it's a function of P capital, which is, of course, can also be written in terms of the small variable, Q small and P small. Transformation equations are given. So let me write transformation. Okay, it sounds funny, trans equation. Okay, trans equations, of course, are given. Let me emphasize on that. Right. Okay, so as a result, we can write this using that, and we can work on this using that. So we can write explicitly what we can get out of that factor and that factor. Okay, so summation over K and partial derivative of L with respect to Q, and now chain rule. There will be additional summation, and I think I used L small. Yeah. So there will be summation over L, and additional bracket, and now let's differentiate this dg with respect to, and of course p we have here and there. So it will be partial derivative of g with respect to q l and dql with respect to pk. Right, so just this. And then of course pk also in the second, in this part. So we have to do the same. So plus partial derivative of g function with respect to pl and partial derivative of pl with respect to pk. Okay, so that's this term. And now let's do the same with the second one. So it will be minus partial derivative of f with respect to, okay, I will add second sum with respect to pk, and then summation again over L and dg over dql and partial derivative of ql with respect to now what? Qk. And plus partial derivative of g with respect to pl. It's now second part. And partial derivative with respect to qk of pl with respect to qk. Right? And conservation of brackets requires me to close this bracket. Right? Okay, it's getting a little bit messy, but not much. Just a few lines. Okay, now, what do we need to get at the end? We need to get at the end Poisson bracket with respect to q small, p small. So where inside of this, there, you remember, there will be partial derivatives df with respect to q, df with respect to p, and so on. So with respect to p and q capitals. So it means that let me get this. Oops, I was planning to use one line. Right. So you see this factor, right? So I want to get terms with that, and over here this, where we have dg over dql, right? And then this term with this factor, it will be my second, right? So let me combine those terms, factoring out, of course, dg over dql and dg over dpl. I guess I'm trying to get that structure, right, which I want to get at the end. Okay, so now let me, and also summation over L must be taken outside, because that will be summation in my Poisson bracket in the new world, right? Because you see we have L here, L there, right? So that will be the summation at the end. So let's take it outside. So, you know what, let me move even closer to the edge. Right, so it will be summation over L, and then probably first I will get, yeah, GL, this term. So partial derivative of G with respect to QL, and probably I will open the bracket. No, first let me put the summation. So now summation over K is inside, and this first. Okay, let me open the second bracket. So it will be partial derivative of f with respect to qk, so this, and this times partial derivative of ql with respect to p sub k. So it's this term. Now that and minus in front. So there will be minus partial derivative of f with respect to pk. So this n times, summation is outside, good. And partial derivative of ql with respect to, no, it's good, it's good. So this and this term we combine. So this bracket is open, this is closed. So now let's take care of these double line terms. Summation, no, let me start, of course, with this, which is we factor out partial derivative of g with respect to PL, and then summation over k, and what will be left I will combine in that bracket. Again, df over dqk and dpl over dpk. So partial derivative of f with respect to qk and partial derivative of ql with respect to pk. So it's from this first sum, and now minus, and the second sum, minus partial derivative of f with respect to pk, it's this, and times that derivative of p capital with respect to p small. Let me separate minus from this sign of ratio. Right. Partial derivative of PL with respect to QK. Right, conservation of brackets. We closed that, we didn't close this. So let me put another bracket. Okay, we see a familiar structure. Look, what about this? F with respect to Q, Q with respect to P, F with respect to P, Q with respect to Q. Poisson bracket and minus in between them. Poisson bracket of F and QL. Cool? Right, so it's a Poisson bracket of F and QL. And of course, written in Q small, P small, right? Still, Q small, P small. Right, which important to emphasize now. And that will be also Poisson bracket, but now between F, oops, something over there is fishy, right? And you didn't tell me. This QL shouldn't be here, it should be PL. That term comes from, yeah, this. Why did I write QL? It should be PL, right? You see. So this term, and for whatever reason, it's a little bit messy, so I'm not surprised that I missed, okay, wrote something wrong. PL, okay, now it's good. So that is a Poisson bracket between F and PL. Oh, no. Of course, with summation sometimes. Okay, with this sum. So it will be Poisson bracket between F and PL, again, in small variables. Okay, so let me rewrite it. Because now what we got, we're going to recycle it twice, and then we will start using it one more time. So there will be lots of recycling, right, in this derivation, right? Okay, so let me rewrite from the very beginning this and equals to what we got. Right, so it will be, so let me rewrite even that left-hand side. Right, QP equals, and now this. So it will be summation over L and dg over dql in Poisson bracket f q l, again in terms of q small, p small, and plus this partial derivative of g with respect to pl, and again Poisson bracket, but now between f and pl in terms of q and p small. And again, conservation of brackets requires me to close that bracket. Okay, so now let me frame it kind of green because it's not final but important preliminary result, which we will, as I said, need to recycle a few times. So let's recycle it. Recycle it twice. Right. Which way? Again, functions f and g are arbitrary. Where here, let me emphasize, the arbitrary functions, right? Of course, well behaved, right? So what if we, for example, instead of function f over in this expression, use, I think first qm. One of, here we have summation over L, so here we have the whole set of Q's, right? One particular Q instead of F. It's not illegal, right? Function F and function G, they describe, it's any function describing our system. If G or if F equals to one of the coordinate, it's still the function which describes our system. So it's not a crime, right? So I think first I use this, yeah. Okay, let me put a small bullet over here, right? First recycling. So what if we let F be QM, one of those QLs? Again, summation over L, we're just picking a particular L equals to M, right? And instead of function G, we're going to use function F. Funny, but it's not illegal, right? Okay, so now let's rewrite it and see what we can get. Maybe we can use those results in order to continue the proof, right? Okay, so now, we will get as a result, so this will be QM, and instead of GF equals, okay, Q small, P small. Mathematicians like sometimes to, okay, actually not sometimes, quite often, to use some funky moves, right? Okay, it's one of those. All right, okay, and summation over L, and so it will be df with respect to QL, and the Poisson bracket between what QM, QL, QM, QL, in terms of Q small, P small, right? I'm just rewriting using these sort of replacements, and plus partial derivative of f with respect to PL, and this is QM and PL in terms of Q small, P small. And again, bracket must be closed. Okay, so at this point, proof should be kind of terminated, and we should digress and spend like maybe 15 minutes showing something, and that something you will do in homework. All right, I think I already posted, and you don't have to do it by yourself, right? Spend, I don't know, weeks doing it, finding it how to do it. My proof is also attached to the blackboard. So what we have to show, look, here we have Q. It almost looks like fundamental Poisson brackets, but except for here, fundamental Poisson brackets, Q small, basically written in terms of small variables. And also all this written in terms of small variables all the time, Q small, P small. But what we have here, we have Q capital, Q capital, written in terms of Q small, P small. So right now we cannot tell that this is zero because it's, strictly speaking, it's not a fundamental Poisson bracket. Because we wrote again Q capitals in terms of Q small, but in order to call it Poisson bracket or fundamental Poisson brackets, it must be written over here in terms of Q capital, P capital. All right. So that's you will have to show in your homework, so that this is equal to, okay, let me frame it, okay, not frame it, sort of circle it, and it is equal to, you know what, probably I'll move to that, this side. Yeah, let me move to this side, put the sign, equal sign, because over there I'll have to discuss that bracket also. So you'll have to show that this is equal to QM, QL in terms of Q capital, P capital. So you will prove in your homework that this Poisson bracket in terms of Q small, P small equals to the same Poisson bracket in terms of Q capital, P capital. And this is, okay, that looks like R. Let me rewrite it. And this is fundamental Poisson bracket in our new variables Q capital, P capital. Basically, it's this, but of course written in terms of Q capital, P capital. But of course, you remember we have canonical transformation equations, so these are still canonical coordinates. So this is correct for our new world of capital variables, right? And so if this is fundamental Poisson bracket, it must be equal to 0. So this is equals to 0. Okay, let me write. So it's a fundamental Poisson bracket. Fundamental Poisson bracket, right? And that is your homework. And again, you don't have to do it. You just need to read my derivation, right? My proof. Right? I just don't want to spend another 15 minutes getting through that. Although it's very important, right? Maybe I will change, or maybe my mind, and next semester I will go through that derivation. It depends. We'll see. Right. So it means that we can dump this. It's 0. Right. This is, again, part of your homework, but I didn't ask you to prove, I think. I just wrote that in a similar way. Yeah, this you will go through the proof. How to, why this equals to that. This, of course, can be done in a similar way, but I think I didn't ask you to do that. Right. So in a similar way, I just wrote that this will be equal to Q capital, P capital in terms of Q capital, P capital. Again, here it's written in terms of small variables, but it can be proven that it is equal to the same Poisson bracket written in terms of Q capital, P capital. And what is this? It's still fundamental Poisson bracket, this one, number 3. And the order is correct, Q first, P second. So it will be just simple Kronecker. So it will be delta ML. And again, so this will be your homework. That will be your homework. And where you'll have to use all generating functions. F1, F2, F3, and then F4, all right, in order to prove this, right? Okay. That again, as you will see my derivation, I will just write in a similar way it can be shown, right? It just will be just lengthy again. Okay, so this is 0, this is symbol Kronecker, all right? And you know what? Let me write it over there, the answer, to save space. All right, so symbol Kronecker is going to kill this sum. All right, so we're going to have, this is 1 basically, and here we'll have partial derivative of f with respect to p m. M is a particular L, value of L, right? So it will be equal to partial derivative of f with respect to p m, right? So that's the result of this, right? Okay, it's almost what we want over here in order to continue using this, right? So here we have QF, here we have FQ. Okay, so what a big deal. We can flip, change index, and we will have a term ready to be used over here, right? Okay, so let's adjust it. Let's adjust it, right? So we will get F QL, right? In terms of Q small, P small, of course, right? So I'm just adjusting this. So I changed order, and you remember properties of Poisson brackets. If you change order, minus pops up. So it will be minus in partial derivative of f with respect to PL. And I switched index M to index M. What a big deal, right? I can do it at any time. Okay, so now we are ready to replace this. Now let's recycle this expression one more time with different substitutions and get something for this Poisson bracket. It will be similar to that. Right? You see, first we recycle this equation twice in order to continue using this equation in our proof. Very finicky moves, right? Okay, so now, so let second recycling, let F now be P capital M. So here we use Q, and so now it makes sense logically to use P capital. P capital M, and instead of again G, I will use function F. And so let me rewrite and analyze in a similar way like we've done it here. Okay, let me write it. So it will be PM, so I'm looking at this, right? So it's a PM F in terms of Q small, P small equals, right, summation over L, summation over L, and now, so it's a partial derivative of F with respect to QL times, then instead of F, it's a PM QL, again in terms of Q small, P small, and then plus partial derivative of F with respect to PL plus partial derivative of F with respect to PL, and Poisson bracket of PM PL. PM capital, PL capital in terms of Q small, P small, and we need to close that parenthesis. And again, basically, these are not fundamental Poisson brackets right now, but it can be proven similar to this. Again, you will prove only this in your homework, but in a similar way, can be proven that this is equal. This equals to PMPL in terms of P capital, Q capital, and that is actually a fundamental Poisson bracket. Right. Okay, so I will write above, so it is equal to. All right, PM PL in terms of Q capital, P capital, and that is fundamental Poisson bracket. But of course, in the new world, or in the world of capitals. Oops, I slightly erased this. And that is 0. Right. So this, the whole second term is 0. And this PMQL, again, it's not right now, it's not a fundamental Poisson bracket, but again, it can be shown similar to this, that it's equal to, that this equals to PM QL in terms of Q capital, P capital. And this is fundamental Poisson bracket, but order you see different. It's a PQ instead of QP, so it will be minus delta QR, minus symbol Kronecker, so it will be minus delta ML, right? So this symbol Kronecker, of course, is going to kill this sum, leaving us only one term where L equals to M. So it will be df with minus df over dqm, because L equals m. That's the surviving term. So let me write it underneath. All right. So it is equal, and as I said, it will be minus partial derivative of f with respect to qm, right? And again, you see, it looks slightly differently what we have here. So, but we can easily adjust it, right? So we have PMF, but we have here FPL. Again, change order. That will give us minus. That minus with this minus give us plus. And instead of M, we can use the subscript L. What a big deal. We can easily adjust this. So adjust it, and we will get, so it's F P sub L in terms of course, Q small, P small equals to, oh, not minus. Minus, as I said, will disappear because we flipped the order. And as a result, we'll have partial derivative of f with respect to ql. All right, so this will go into that. Okay, maybe I will show that this will right. This line will be longer, but you understand it will go there in a similar way. So now we can go back to this. That's why I framed it, because we recycle it twice, and now we go back to to the same expression to continue the proof. Right. Okay, so I think I can erase this. Yeah. Okay, I can erase all the way to this, to the beginning of this proof. And yeah, so back to, maybe I can put here asterisk. Right. So back to that. And so I can start rewriting it f g in terms of q small, p small. It's our beginning original, equals to summation over L, a partial derivative of f with respect, wait, no, g. I was looking at this, no, this. Look at the wrong line. So partial derivative of g with respect to ql. And instead of this Poisson bracket, of course, we have this prepared ingredient minus partial derivative of f with respect to pl. Okay, then plus partial derivative of g with respect to pl. And instead of this Poisson bracket, we prepared this ingredient, right? Yeah, exactly the same. So it's a df over dq L capital, right? Right. Look awesome, right? So now we have only capital variables, nothing else. And of course, order, this should be actually first, all right, and this should be second. Okay, let's rewrite it. Although I didn't feel like fg equals to summation over L, and so this should be first, this term actually. Poisson bracket of f and g, but now in terms of q capital, p capital. And of course, so yes, Poisson brackets are invariant, but again, under canonical transformation. If you pick some strange transformation which is not canonical, then who knows, right? We didn't prove that it would be different. We didn't prove that it would be the same. So we just cannot tell anything for any transformations. But for canonical transformations, Poisson brackets are invariant. Their values stay the same, which is nice. This is an important part. All right, so now your homework. So now I will write these results which you're going to prove in your homework, because now in order to develop the set of tests that we have to use in order to convince that a certain transformation equation is canonical, we need this, your homework results. Okay, so let me write. Yeah, another thing which I actually was planning to mention, but I forgot. I looked at my notes. So now, since Poisson brackets are invariant under canonical transformation, so very often we can just drop the subscript. Actually, here I already dropped the subscript. It's subconsciously Q P, right? So Q small, Q capital, P capital. But now, since we know it's the same, we can drop the subscript if you don't feel like wasting time in ink. Right. Okay. Okay, so let me write down the results which you will prove in your homework, because we need them. I really, really desperately need them. Okay, so now let me write. You know what? I just again look at my notes. What you are going to prove? You're going to prove that fundamental Poisson brackets, basically what fundamental Poisson brackets are invariant under canonical transformations, right? Basically, a special case of what we proved just now in general, right? So basically, you will be messing with canonical, no, with fundamental Poisson brackets. Fundamental Poisson brackets under canonical transformations are invariant, right? So that's what you will prove. Okay, so now let me write. So in your homework, you will show that fundamental Poisson brackets are invariant, also are invariant under canonical transformations. Under canonical transformations. Right. And so now let me write them down. So the first one, probably with QQ. Let me write that down. Yeah. Right. So Q subscripts, which I use I and J. Okay. QI, QJ. We said J, wrote F. All right. In terms of Q small, P small will be equal to Poisson bracket of QI, QJ in terms of Q capital, P capital, and of course, since this is fundamental Poisson bracket, right? So this is 0. So that's what you're going to prove, and the rest you can write in a similar way. It can be shown, right? So now let's write the rest. First, I will write what for P. Okay. P I P J in terms of Q small P small equals to Q P capital. Q capital P capital equals to 0. And the last, so QI Pj in terms of Q small p small equals to QI Pj in terms of Q capital P capital equals to, I wanted to write 0, but of course now it's a symbol Kronecker, of course, delta Ij. Delta Ij. It looks like I need to change marker soon. Just whenever I change it for the next 5 minutes, the stuff written for the next 5 minutes will be difficult to erase. Okay, so now this can be used to as a test if you want to convince yourself that a certain transformation equation is canonical. Okay, so let me write. So now the most convenient way to decide whether a given transformation is canonical. So, okay, let me first show what's the idea, right? So if you write, okay, let's assume that you have some transformation equations, right? And you don't know if they're canonical. So what you do, you just use this. So you just write Q capital in terms of Q small p small, Q capital in terms of Q small p small. And if this is equal 0, the first 1/3 of the test, it will pass. If then goes to the second, if you write P capital in terms of this, P capital in terms of this, and if it's still 0, that's the second part of the test. And then if you go over here and again construct the same Poisson bracket Q in terms of Q small p small and P in terms of Q small p small, and if that is delta symbol Kronecker, then that's the last part. And if all of them are correct, then you can say, yeah, that that transformation equation is that transformation is canonical. Okay, that's what I was looking for. That transformation is canonical. So let me write that down now. All right, so it provides the most convenient way. Okay, I need to erase this. And in your homework, you're going to have a couple of examples, right? But this is usually the easiest part, right? Okay, I will probably use blue. So this it provides, or maybe these equations. Okay, these. Okay, it provides. Let me just use my notes. The most convenient. It provides the most convenient way to decide whether a given transformation is canonical. Convenient way to decide if whether, it doesn't matter, if a given transformation is in fact canonical. Is canonical. Actually, it's not the rule, it's basically a title, right? I shouldn't be framing it, but okay, not a big deal. So as a result, let me write these 3 steps in this test. Right. All right. So as a result, the first one, number 1, Q subscripts I. Still I use here I written in terms of Q small p small. Right. You know what? Probably I should Okay, so let's assume that transformation equations are given, right? So let me over here probably write. So qi equals to qi in terms of q small, p small, and t, and pi. Okay, so that is a candidate. Okay, or yeah, these equations are candidates, or this transformation is a candidate to be canonical. So you want to convince yourself, prove. So you grab them and start dragging through those three conditions. All right, so first this paired with qj, which is a function of q small, p small. And if this is correct, that's the first part of the test. Then, yeah, I didn't close the bracket because it looks so weird. Now the second. All right. So based on this, pi written in terms of small, then pj in terms of small variables. If this is also 0, okay, the second part of the test. And now the last one, usually that's you have to calculate. Quite often these are automatically 0. And now qi pj, and it must be equal to symbol Kronecker. So these are 3 steps, right, in this proof. Okay, let me, of course, frame them. And let's look at the example. Okay, good. Okay, and now it's time to erase this beautiful mess. Yeah, I need space. Right. I guess I will be able only to finish the example. But usually the problems about these proofs are the easiest, right? So the example. So what if we have these transformation equations? So P capital equals to square root of 2m omega P small times cosine of q small, right? So it's a P capital. Generalized momentum, momentum it's 1 in the new world, right? And then generalized coordinate in the new world, that is square root of 2p divided by m omega n times sine of q. So these are candidates. We want to convince ourselves that these equations give us canonical transformation. Do they remind you of anything? You remember our struggling? Okay, my struggling. You just observed that, my struggling, right? When we tried to solve the damn simple problem, harmonic oscillator, using canonical transformations, right? Do you remember how much of funky moves I had to make in order to construct those generating equations, right? And then we try to satisfy those equations which are supposed to give you canonical transformations, right? So basically, yeah, that's those transformation equations. Of course, we know that this will be canonical, right? But we want to prove, we want to see that, of course, it will work. It works. It works. Okay, so of course you remember Poisson brackets. Yeah, we still have them. by definition. So now let's massage, let's drag these two equations through all those three conditions. Right, let me separate that. Right, and so the first one, test number one, of course, Q, which we wrote just a Q capital, of course, in terms of Q small, P small. Okay, so let me write explicitly. Summation, yeah, I'll drop summation. So partial derivative of Q with respect to Q small. Plus Y, there's no summation, it's a one-dimensional system. Which summation I'm talking about, right? It's a force of habit, since every time we have n variables. So then partial derivative of Q with respect to P small, then minus partial derivative of Q with respect to P small, and partial derivative of Q with respect to Q small. Identical is 0. Right? I don't have to even calculate those derivatives, right? Because order doesn't matter if you differentiate first this with respect to P and then with respect to Q, or you flip the order, it will be the same. So every time these two terms, they cancel each other, right? So quite often situations will be like this, right? So identical is 0. First check mark. Now the second will be also the same like the first one, but of course now it's for P capitals in terms of Q small, P small, and the same. Oops, not identical. Not exactly the same. Second check mark. Right. Again, usually most of the time, first and the second equal to 0 identically. But the last one, yeah, usually you have to go through some simple differentiation. Okay, I need to invade more. And so now Q P, of course, in terms of Q small, P small. Okay, so now we have to carefully write it down and differentiate. So partial derivative of Q with respect to Q small, partial derivative of P capital with respect to P small, right? And then minus changing order with respect to P first, and then P capital with respect to Q small. Q capital with respect to Q small. It's a sine of Q, so it will give us cosine, right? That factor and cosine. So it will be 2P over M omega cosine of Q. Then P capital with respect to P small. So 1 over 2 appears, and a square root of P will appear downstairs. So it will be 1 over 2. Okay, let me write it this way. So it will be square root of 2m omega. Then downstairs it will be 2 and square root of P. Right? I think that's correct. And now minus Q with respect to P. Okay, so again, 1 over 2, then square root of 2 and m omega P. Okay. I forgot what? I forgot. It's what? Derivative of P capital. Cosine of Q. Right? Right. Focused on differentiation, so I forgot cosine function over here. How can I squeeze it? So cosine of Q. Right. Okay. So this I differentiate Q capital, so it will be sine Q. Right. and times now derivative of p capital with respect to q small. Oh, that's simple, right? So it will be that factor minus n sine. So it will be minus square root of 2m omega p and sine of q. Okay, I think I didn't make any hope I didn't make any mistakes. So now let's start canceling. So first of all, cosine give us cosine squared. Sine and sine give us sine squared. Minus and minus plus. Then here we will have square root of 2 downstairs. Here square root of 2. Square root of p, square root of p. Square root of m omega, m omega. All these factors gives us 1. This whole construction, it's just 1. So you see I excluded cosine. And similar should be out of this. Right, so let's see. 2 give us, can be cancelled with these 2, m omega p, yep, also 1. So I didn't make any mistakes, so 1. So yeah, we're getting, as a result, cosine squared q plus sine squared q equals to 1. Okay, the last check mark, and done. So yes, true, these transformation equations provide or give us canonical transformation. Right. So it's yeah, as I wrote here, it's the most convenient way, right, to prove using the fact that Poisson brackets are invariant. Actually, in this case, we can say even more specific that fundamental Poisson brackets are invariant under canonical transformation. So we use that fact to develop this procedure. Okay, so we still have a couple of minutes. There's a second example, but it's basically the same, right? All right, so next class. Enough about canonical transformations, enough, right? So next class we will start developing Hamilton-Jacobi theory, right? And again, I will give you that I have a dream speech. Where should we go to make our life easier, right, in terms of solutions, right? Well, I already gave you that speech, but we didn't stretch to the fullest the process of simplification, right? So the process of finding the best possible place on the face of the earth, right, in terms of solving problems, right? So we will try to go to, of course, using every time only canonical transformation. So we don't want to end up in some creepy place, right? So we want to go to a nice place, right, where Hamilton's equations are correct. And the idea is, what if we go to a new world and new Hamiltonian will be just 0? That will be the ultimate simplifications. You will never be able to find any better places, right? And around that idea, so that we want to go to the world where Hamiltonian, that new Hamiltonian, is 0, the whole procedure, the whole Hamilton-Jacobi theory is developed, right? And of course, immediately, of course, it's still, it's a canonical transformation. Still, Hamilton's equations are correct in that world. And if you imagine those equations and k equals 0, you immediately see that in that world, coordinates constant, generalized coordinates and generalized momenta also constant. Basically, it's a gift-wrapped solution. Your goal is just to go there, pick it up and come back. But this traveling, usually traveling is fun, but in this case, traveling can be really painful, right? It's like trying to escape from Cuba on a small boat, right? Fishing boat, right? Something like this. Yeah, it can be challenging, right? But solution, you know what, before you go, you know what, What is an example? So what that can be? For example, that new world where your solution is constant. Initial conditions. So basically, you're trying to find the solution at some arbitrary moment of time, right? T. And in order to get that, you travel to the initial, back in time, right, to the initial conditions, right? Basically, yeah, you will get constants, and at the end, when you go back, those constants will be your constants of integration. Basically, yeah, it's an example, right? So you go back in time to the initial conditions, find the solution in that world, and then go back, right? Funny, right? Okay, guys, thank you. So that will be our next class. So we will start playing with this Hamilton-Jacobi theory. It's very elegant, actually, right? And at the same time funny. At least I find it. Okay, guys.